Okay, so this is my intro for crash course into motion. Um, so this is like a sort of like a assumed knowledge. Like I'm just filling you in on the assumed knowledge in motion in general. Anyway, say if I have like a displacement time graph, right? Vertical line, horizontal line, okay, and I have me some displacement time graph, right? So this is my position or displacement, d. I'll call this, instead of d, I'll call this x, and I'll call this my time, t. Yeah? And this is like my straight line going up, yeah, up and across, right? So over time, my position like moves further and further away from my starting point. What does the slope of this line mean? The slope, the rise over run of this line represents my velocity. How fast am I changing my position per unit of time? So for a straight line, finding the velocity isn't hard at all. You just take a certain amount of time, you see how much has it risen, and then you just figure out what the slope is, rise over run. But this isn't so clear for other graphs like these curvy graphs, right? Imagine my object or me if I was traveling in a weird way. Say I was accelerating much more in some points and not so much in others. So then what I would have to do is I would have to take a tangent to these. And so I would take this tangent as my instantaneous velocity, my instantaneous speed. So at a certain given point of time, I would have to this would be my speed. And this would be sort of the thing that I'm reading from my speedometer. Yeah. So at this point, then I would have a very slow speed, probably still by the looks of it. And I would have here a very, very high speed, very high velocity. So then if I wanted to represent this isn't exactly the slope of a line, like if I'm given this curve. I would have to take the derivative. And that's how I can represent my velocity is equal to the derivative of x in respect to time. Okay. This also carries forward in terms of acceleration. So now I want to figure out how much my velocity changes in respect to time. So just like how I have a displacement time graph, I'm going to have a velocity time graph. And imagine, for example, we'll have this as a straight line. That's my 10 out of 10 straight line. Okay, now this, my acceleration, is how much my velocity changes in respect to time. If I have 1 unit of time, how much does my velocity increase or decrease? I mean here. So in this case, with a straight line, it would again be rise over run. Again, the gradient of the line. But again, if we have curvy graphs like these, this isn't so clear anymore. We would have to take the derivative to find the instantaneous acceleration. At any given point in time, how much is my object or me or the particle or whatsoever is accelerating, right? Okay, so I have A is equal to dv dt, how much my velocity changes in respect to time. Yeah, so again, these are like instantaneous slopes, if you want to think about it that way. So the different way that we can notate this is as x dot. Remember, a dot is different to a dash, like if you have a y dash. A dash usually refers to like any generalized derivative, depending on the equation. If you have y is equal to, I don't know, x squared, then you write y dash is equal to 2x or something, right? And so this is depending on the question. When you have a dot, that is specific to time. So you can't use a dot anywhere. A dot is always specifically to differentiating in respect to time. Good to get this cleared up. So now, if v is already a derivative in itself in respect to time, I can represent this as d on dv, not d on dv, d on dt, or v. This is like a fraction in some sense. So then I can represent as d on dt of that. I can substitute this back in. Dx on dt. Okay. then if I'm going to treat this as vaguely like a fraction, I can have a d squared x on dt squared. Often mathematicians just drop the brackets and we just write it as d squared x on dt squared. But again, what this shows is that acceleration is a second derivative of my position. X represents a position, specifically in the x-axis, but like that's a technicality that we'll get to later. So I can represent this instead of a single dot. Now I'm differentiating twice, so I can represent this as x double dot. Not hard to figure out. If I differentiate with respect to time again, I'll just have a triple dot and so on. However many dots I can fit in front or on top of the x. But this is the basis of motion in general. Okay, so then if I want to differentiate, so let's put out different levels on. So if I had a position or displacement is how far objects have moved. Again, this is like a distance or displacement. Yeah. Okay, that's my, you can say this is a bottom level, even though I'm writing it on top. This is my velocity. So I can write this as x or y or whatever variable I want. And I can write this as x dot. This is my next level. How something, it changes if time changes. Acceleration. And this would be x double dot. Yeah. Not hard to see. So then if I want to go from one to the other, to the next one, like moving up the level or down, whichever way you want to go, in one direction, you have to differentiate with respect to time. Again, here, to get to from velocity to acceleration, differentiate in respect to time. So to move from acceleration back to velocity, you do the opposite, right? How we do the opposite of differentiating in respect to time is integrating in respect to time, so dt. Again, from velocity to position, again you integrate in respect to time. That's this is just like a sort of cycle. This is kind of like converting units in some really vague sense. If I have centimeters and meters, we just divide by 100, and here we multiply. Here we multiply by 100. So it's like, in a vague, really vague sense, this is sort of what happens. A very similar fashion to this. You can take this as a weird analogy. But yeah, this is how this goes. But okay, now to the next step, right? What I wanted to hit home here was this concept called projectile motion. Okay, so about this this thing, right? This thing was like first figured out in like what, the 1600s or something like that. There was this guy called Galileo, and he figured out that if I had any diagonal motion, I can split this up into a horizontal part, and I can split this up into a vertical part. Horizontal, vertical. Yeah. So Galileo figured this out, and this vertical part and the horizontal part, they're independent of one another. They don't affect one another directly. But when you add these two together, you end up with the diagonal part. Working with my vertical and horizontal parts independent of one another can be much more powerful as a tool to figure out anything about an object's motion. So say if I shot a cannonball off, so I had my small cannonball and it was shot out, yeah, from this imaginary cannon, yeah, and and I'm going to assume that it follows this special projectile motion. Again, there's specific rules and regulations that we're working with in this projectile motion, but again, this diagonal velocity that it has, it can be split into its vertical and horizontal parts, and each work differently, a little bit differently. So, working with all projectile motion, it all stems from two simple assumptions. My first assumption is if I have my x-axis, so if I'm going to draw me some axes here, my vertical y-axis and my x-axis, right? So this is like a diagram of what I'm seeing with some axes, yeah? Okay, if I had my x double dot, is equal to 0. What this means, in a very visual practical sense, is that this object, this projectile, isn't speeding up horizontally or slowing down horizontally. So my initial horizontal velocity is going to be the same throughout my entire projectile motion. From the time it's launched till the time it lands, it's going to have the same horizontal velocity. That's what this means. The next one that I have is y double dot is equal to minus g. G is a constant like pi or e. They're just constants. They're just a number. Usually this is 9.8, but it can be approximated to 10. Yeah. There's a negative sign, which indicates that usually we're taking the positive as up, so negative would be counted as down. And so what this represents is that my vertical velocity is always changing. This projectile or object is being pulled towards the ground at g meters per second per second. So its velocity vertically is changing. That's what this means. And the amount that it changes is represented by this number. Yeah. Often in maths, we just leave it as g, but you can sub in our value to get specific numbers if we're required to. But like, again, like, in trig, we always leave it as pi, or, like, times pi or pi over 2 or something like that. You always leave it as pi, even though we know what pi is, which is like 3.14 or something like that, right? So we just like leave it as such. Often it's much easier and less clunky to leave it as g. But again, it's useful to know that g is either 9.8 or 10, depending on what the question asks. In an exam situation, often you would use g as 9.8, so minus 9.8. Yeah? Okay. This is my two assumptions. From this, I can derive practically anything, any piece of information that I need to about this projectile's motion. What is its angle at a given time? What is the maximum height that it reaches? How far does this projectile get launched? Say if I'm like shooting a cannonball and I wanted to hit a target, I need to figure out how far can it reach? What's its range? If I have like, I don't know, like a goalpost that I'm kicking past, like will this clear the post? Or if I'm hitting a tennis ball, so this can be applied to a range of situations. That's what this is very useful for. Okay, working onwards, I can have x double dot is equal to 0. And remember, this is an acceleration of some sort. So to go from acceleration to velocity, we had to integrate. Again, in respect to what? In respect to time. Let's do that for both of these. So integrating this, that means integral of 0 dt. Actually, I'll write this as this way. X single dot is equal to the integral of 0 in respect to time. This is just a constant. I'll call this constant 1, C1. Okay. This constant 1, what this constant 1 represents is my horizontal velocity, like throughout the whole motion. Remember, I told you that the horizontal velocity doesn't change. So then this C1 is that horizontal velocity. Usually this horizontal velocity is can be calculated as the horizontal part of this initial diagonal motion. But it can also work, say if I'm like launching something across from a building, that horizontal velocity will be the C1 as well. Okay, for this part, integrating y single dot is equal to now the integral of minus g in respect to time. This just gets me minus gt plus, I'll write this as c2. Okay, what this c2 represents is this vertical velocity. When my time is 0, so when t is equal to 0, what is my vertical velocity? That's what y dot represents, my vertical velocity. X is horizontal, y is vertical, like x and y axes. So now my y dot is my vertical velocity, and c2 represents what it is when time is 0, when I just start shooting it out. And that's what this vertical arrow represents, when I split my diagonal vector into a horizontal and vertical part. Okay, that's cool. Now I have my x as it is, and now I have to integrate once more. Integrate c1 dt, which is just c1t plus another constant, write this as C3. 1, 2, I already used those up, so I'll write C3. Okay, now I told you what C1 is before. What C3 represents is where do I start off when time is 0. So now imagine this is my origin, as this diagram shows, and if I'm launching something from the from a distance, this distance, away from the origin. Often, in most cases, when we're dealing with questions, this C3 will go to 0, but this is just a useful piece of information for your understanding. So this C3 just represents when I start off, how far away from the origin am I in the x-axis or in the x component. I can start shooting from up here as well, but this C3 value would be the same for this point and this point because they both take the same x value. Yeah. Yeah. Again, in most cases, this would be 0 because most people would tend to keep their origin at the place where we're shooting from. But if I have multiple projectiles, then this so then I would have to have one of them at the origin and the other one would have to be a different spot, and so then this C3 will be useful. Okay. Again, you would solve for C3 depending on where you start off when time is 0, and this is what you call your initial conditions. Initial means starting. Starting is when t is equal to 0. Again, my initial conditions is where x is when time is 0, and that's what C3 represents. Okay, if I have my y as it is, now I have to integrate once more. I have minus gt plus c2 dt. Okay, integrating, then I get minus g t squared on 2 plus c2t plus c, now 1, 2, 3 is already used, I have 4, c4, now my fourth constant. Okay, now this constant in the y equation, now instead of representing my horizontal displacement where I start off from, this c4 represents my vertical displacement where I start off from. So now you can read all of these like sentences in some sense. So C4 represents where I start off from when I shoot, away from the origin. So say if I'm like shooting from like a cliff or a building or some sort, and I'm shooting a projectile off, right? Now if I let my origin be at the base of the building, this height of the building would be my C4. How far away from my origin vertically am I launching from? That's what C4 asks, or what it represents. When my time is 0, what is my height? Yeah, so when I'm just starting to shoot, what is my height? That's what all these 6 equations represent. And using these 6 equations, I'll just write them again. X double dot is equal to 0, y double dot is equal to minus g, x single dot is equal to c1 t plus c3, no, c1t, c1, sorry, c1. X itself is equal to c1 t plus c3. Y single dot is equal to c. Again, these c1, c3, c2, sorry, minus gt plus c2. These constants are just labels for arbitrary numbers. Minus gt squared on 2 plus c2t plus c4. Okay. So again, C1, C2, C3, and C4, they're just random constants representing some fixed number. This number does not change, but it is unique to every projectile motion, unless 2 projectile motions are identical. But yeah, these are your 6 equations which you'll be using. In most exams these days, you'll be given a formula to work with, but deriving these equations gets to the heart of what projectile motion is all about. Yeah.